In modern database systems, every millisecond counts. When an application asks for a record, the database often has to traverse multiple layers of memory and storage to find it. The most expensive operation is a disk read. Even with high-speed NVMe drives, fetching data that isn't in memory is orders of magnitude slower than a cache hit. But what if we're looking for something that doesn't even exist? In a typical system, the database might spend precious time searching its indexes and pulling data from the disk, only to come back empty-handed. This is the negative result problem. We are wasting resources just to find out that there is nothing to find. Today, we're looking at a probabilistic data structure designed to solve exactly this, the Bloom filter. It acts as a gatekeeper, telling us instantly if a record definitely does not exist.
A Bloom filter is what we call a probabilistic data structure. Its job is simple. It tells you if an element is a member of a set, but it has a very specific way of answering. If the filter says no, it is 100% certain. The item is definitely not there. You don't need to check the disk, you don't need to check the cache. You can return a 404 immediately. However, if the filter says yes, it actually means maybe. There is a small chance, called a false positive, where the filter thinks an item exists when it doesn't. Because of this asymmetry, we call it a no machine. It's designed to filter out the definitive negatives with zero disk I/O, only allowing the potential positives to proceed to the expensive storage layer.
Under the hood, a Bloom filter is incredibly space efficient. It doesn't store the actual data, like usernames or IDs. Instead, it uses a simple bit array of size m. Initially, every bit in this array is set to 0. This simplicity is why Bloom filters can fit millions of entries into just a few megabytes of RAM. Unlike a hash set, which stores the actual keys and grows with the size of the data, a Bloom filter's size is fixed. You decide how many bits to allocate based on how many items you expect to track and what false positive rate you can tolerate. By decoupling the data from the representation, we gain massive performance at the cost of a tiny bit of uncertainty. To map an item into this bit array, we use hash functions. But a single hash function isn't enough. It would lead to too many collisions. Instead, a Bloom filter uses k different independent hash functions. When we want to add an element, like the string Alice, we run it through all k hash functions. Each function produces a different index in our bit array. The key here is that these functions must be fast and distribute values uniformly across the array. Common choices are murmur hash or city hash, which are optimized for speed rather than cryptographic security. By using multiple hashes, we create a unique fingerprint of bits for every item, making it much harder for two different items to accidentally light up the exact same set of bits.
We take our input, Alice, and compute 3 hashes. Let's say they return indices 1, 4, and 7. We go to our bit array and flip those specific bits from 0 to 1. Now, Alice is represented in the filter. Notice that we didn't store the letters ALICE anywhere. We only flipped bits. This is a one-way street. Because multiple items might share some of the same bits, you can never remove an item from a standard Bloom filter. If you tried to turn Alice's bits back to 0, you might accidentally delete Bob, who happened to share index 4. This is a fundamental trade-off. In exchange for massive space savings, we lose the ability to delete.
Now, how do we query it? When a request comes in for Charlie, we run Charlie through the same k hash functions. Let's say they point to indices 2, 4, and 8. We check those positions in the bit array. If even a single one of those bits is 0, we know for a fact that Charlie was never added to the filter. This is the definitive no. We don't need to look any further. However, if all the bits are already set to 1, the filter returns yes. But wait, did we actually add Charlie? Or did a combination of Alice, Bob, and Dave happen to flip those specific bits already? Because we can't tell the difference, we must treat a yes as a maybe and proceed to check the actual database. False positives are the price we pay for efficiency. As the bit array fills up with more and more ones, the probability of a false positive increases. If every single bit in the array were set to 1, the filter would say yes to every single query, becoming completely useless. This is why we must size our Bloom filter correctly. The probability is a function of the number of items, the number of bits, and the number of hash functions. If you want a 1% false positive rate, you typically need about 10 bits per element. If you can tolerate 10%, you only need about 5 bits. By adjusting these parameters, engineers can balance memory usage against the cost of occasional unnecessary disk reads. You are likely using Bloom filters every day without knowing it. Google Chrome uses them to identify malicious URLs. Instead of storing a massive list of millions of dangerous sites on your laptop, Chrome stores a compact Bloom filter. If a URL you visit isn't in the filter, it's safe. Only if the filter says maybe does Chrome reach out to Google servers for a full check. In the database world, Apache Cassandra uses them to avoid checking SS tables on disk for keys that don't exist. This drastically reduces read latency. Similarly, Postgres uses them in join operations to quickly discard rows that have no match in the other table. They are the invisible efficiency layer of the modern web. So when should you use a Bloom filter? They are perfect when you have a massive data set, high read volume, and expensive storage access. If your data fits entirely in memory, a simple hash set is usually better because it has 0 false positives. Remember the constraints. You cannot remove items, you must handle the maybe case in your logic, and you need to pre-allocate the size. If you need deletions, look into variants like counting Bloom filters or cuckoo filters. But for the vast majority of no machine use cases, the classic Bloom filter remains the champion of simplicity and performance.
Bloom filters prove that sometimes a maybe is good enough if it saves you a trip to the disk. By embracing a little bit of uncertainty, we build systems that are faster, smaller, and more resilient. Thanks for watching.